Good morning. I would say ladies and gentlemen, but we're kind of short ladies and gentlemen, so we just have to have a lady and gentleman. Today we're going to start on note card 34. So I want you to open your packet to 34, optimization problems. Do you remember a while back we did something called the extreme value theorem? And if you can remember back that far, what were the things that we evaluated as far as extreme value theorem? What were the values that we used, and what did we call those values, or how did we demonstrate those values and categorize them? Okay, you look for a minimum. So extreme value theorem tells you that if a function is what in a domain? If a function is
n.
What did you say?
N.
In. How about continuous? If a function is continuous in a domain, there has to be an absolute maximum and an absolute minimum, right? And how do you find what your candidates for absolute minimum and absolute maximum are? What are your candidates? How do you determine your candidates for an absolute minimum and an absolute maximum?
Theorem? No.
Okay, well, the thing about it is, now you're right. Okay, we're going to get back to, so just park that thought. I think you're kind of thinking the right way. But we'll talk about that, but even more fundamental. So I think you're going to the next level. But right here, you find the endpoints, right? Where the domain starts, where the domain finishes, and what about in between? What are your other numbers you consider in between? What are those called?
Oh my goodness.
What are those numbers called? There are certain kinds of numbers that you put on a number line.
A point?
Well, no, not a point. We're talking just about x values. Critical numbers, thank you. Yeah, so remember, see, critical numbers. And critical numbers occur, how do you determine what a critical number is? Where the what?
I remember writing this down, but I don't remember how to do it.
Okay, so Gavin a minute ago was talking about zeros, right? So it has to do with zero. So how do you determine a critical number? Where what is equal to zero? No. No, not function, the what?
What's it called?
Okay, how about the first derivative of the function is either equal to 0 or equal to 0 or undefined, yes. So
I go through all my words in my brain.
that's right. So that's what we're doing. That's part of what we're trying to do in this class. We're trying to reach back and pull things and kind of assemble them, bring them from the past into the present. And so basically what optimization problems are, they are real world problems with using the extreme value theorem. And
I remember that being too hard, so maybe listen.
yeah, so to me, the hard thing about this is the translation and the articulation to get to that point out of word problems. Are you a big fan of word problems?
I hate word problems. I can't read them. I can't.
Can't read them? Can't, yeah. So basically word problems really are translation problems.
Oh man.
And so we're trying to translate the English into algebraic symbols, okay, equations and relations and so forth. So that's what we're doing. But there are key words, and we're going to use this. Now here's the first problem they give us. A particle moves along the x-axis, so its velocity at time t is given by a differential function whose graph is shown below. And so here's the differentiable function v, whose graph is shown below. Okay, so here's the graph of that function. And the velocity is 0 at t equals 0. And at t equals 3 and t equals 5. And the graph has horizontal tangents at t equals 1. So this is so here we have a horizontal tangent right here where t equals 1. And also where t equals 4. So at t equals 4, we also have another horizontal tangent line to the tangent there. And the areas of the region bounded by the t-axis in the graph of v on the intervals 0, 3, 3, 5, and 5, 6 are 8. So that's 8. This is 3. And this last piece here is going to be 2. At time t, the particle is at x equals negative 2. So for t between 0 and 6, find both the time and position of the particle when the particle is farthest to the left. Justify your answer. So how would you do that? So we're given a graph of velocity, so we're using velocity to determine position. So we want to find out the time and position of the particle when the particle is farthest to the left. So what do you set up for this? You set up a table. Here's your candidate test, right? So what are your numbers of evaluation? You're going to have t, and this is v. We're going to call it x of t. So what are the values we put in here? Okay, the values are the endpoints and the critical numbers between the endpoints. What are your endpoints? 0 to 6. Okay, those are your endpoints. And what are the critical numbers in between? So 3 and 5. So what is our position where t equals 0? So negative 2. Okay. So let's go ahead and fill in here. So what is going to be the value at 3? What's going to be our value at 3? Okay, let's look at this. You got a number line right here. Your critical numbers here are 3, 5, well, 3 and 5, and the end point is 6. So you got your velocity here. You have your x position here. So what happens between 0 and 3? Positive or negative? Negative. So what's the thing doing between 0 and 3? X is going down. Now how much does it go down? What number do you see that shows how far x goes down? Which number? I'll give you a hint. It's either 8 or 3 or 2. Which number shows you how much it goes down?
2, 3.
Okay, we're talking between 0 and 3. So 8. So if we go down 8, what is it going to be over here? So negative 10 goes right here. Okay, next, between 3 and 5, is velocity positive or negative? Positive. And so where do we end up here at t equals 5? Okay, we're going up between 3 and 5. How much do we go up? 3. So what goes here? So negative 7 goes here. And then between 5 and 6, so we have negative 9. So the time and positions, what's the time and position when the particle is farthest to the left? When is the particle farthest to the left? Okay, at t equals 3, right?
Yeah.
And it says, and that's going to be position equals negative 10. And it says justify your answer. How would you justify this answer? Yeah, that's a harder one because you can see what it is. You can say that.
I can see why, I just don't know how to put that into words.
You can say that there is a relative minimum at t equals 3, right? So relative minimum at t equals relative minimum of negative 10 of negative 10 where t equals 3 and all other candidates are higher or something like that. All other critical numbers and candidates, all other endpoints and critical numbers are greater than negative 10, right? And critical numbers are greater than 10, greater than negative 10. So that defines it. So that's how we know that we have that. And it's just on the graph. You can see that. But it's the same thing we did absolute value or extreme value theorem. We just had these candidates and you pick off which ones of these are the maximum minimum. So that's all that is. Okay, let's go on and look at. Now I mentioned we had, these are like real world situations. That was not especially one. That was a calculus problem from an AP test. But if you look over here, we have some kind of a structure of the problem. So here it says, okay, at times in life we're asked to do an optimization problem, find the largest or smallest value of some quantity that will fill a need. Whether it's to find the route to drive, building a structure with the least amount of material, enclosing space. So basically it's dealing with limited resources to come up with a solution to something. And you're always looking for a quantity to be maximized or minimized. So in solving word problems, you look carefully for certain words along all that. Minimize area, smallest volume, least amount of time, shortest distance, cheapest price. And on the following pages, there are a wealth of problems. Quickly examine each and underline the key words which tell you what kind of problems it is. So really we're going to do the exercises in the translation here. And I will tell you that this is the kind of thing that I have to get in the frame of mind too. I'm experienced looking at these things, but they're hard to see. Okay, and then they give some more things about assigning variables. Okay, using letters. Sometimes you can use letters that aren't necessarily X and Y. Making a sketch, maybe making a chart to show relationship. You'll see, most of the time you'll see some kind of formula or formulas that'll tie things together. Then it says, then it just goes down the process. And if there's more than one variable on the right side, you might have a secondary equation or restraint. And then this one right here is where you get into the calculus, where you take the derivative and set that derivative equal to 0. And then you look to see if you have a relative maximum or minimum. And then you should be able to answer the question, you hope, based on that. And yes, you can use your calculator too. Sometimes you can verify this in different ways, so we're going to do some of that. Now here's an example of a situation where you have two numbers that add up to 40. And so you just try different numbers. You try to find the numbers that maximize their product. So this is not an equation way of doing it, but this is just a trial and error way of doing it, where you just pick out different things. You pick out a smaller number and a larger number and just sort of work back and forth till you find the product. So based on the trial method that you see here, two numbers adding up to 40, which two numbers, which when multiplied together, give you the maximum product? 20 and 20. And so does that kind of make sense? Yeah, it should. And this is an example of really how graphically you can verify, you can use trial and error to do these sorts of problems. But what happens, you have an equation here. I'm going to try to write this out and just sort of work it through, so help me with this. So what you're looking for in this case are going to be two equations. And what equations would you use for this? What equations could you use? What are you looking for? There are two things involved here. What are those things? Okay, so add to 40, so how would you write that? What equation would you write out? Okay, can you just talk a little bit? I can't barely hear you. Go ahead.
So, what do you like? something plus something else equals x plus y equals 20.
So maybe like x plus y equals 40, is that what you're saying?
Yeah.
So let's try that. Right, so x plus y equals 40. And then what would be your secondary equation? Secondary equation would be,
That's when you define the product.
yeah. So you'd have, you're trying to maximize the product of x and y, right?
Mm-hmm.
You're trying to do that. So how would you get all this into one equation that you could use?
Oh,
How about x equals 40 minus y? And then we could plug that into here. We can plug that in for x. So we have our area, which is what we're trying to maximize, is equal to 40 minus y times y. Okay, what next? We're trying to maximize, so we found our equation here. So we come back here to our steps here. Okay. So let's go here and do this. So what is going to be our derivative and set this equal to 0? Okay, so we have 40 minus y times y, so what is that going to be? 40y minus y squared. So we take our first derivative of that, what are we going to have? So 40 minus 2y, and if we set that equal to 0, we should be able to solve our equation. So we solve our equation, what do we come up with? 2y equals 40. So y is equal to 20. Okay, so that's one. So that's going to be our critical number, and we want to maximize. We can go ahead and put our critical number just to verify. If we put our critical number here, we say our area is going to be this, and our value of y is going to be our input value. So if we choose y less than 20, what do we get? We get like 10. So we'll get 40 minus 2 times 10, that's going to be positive, right? So area is going to be increasing all the way up to here. What about a number greater than 40? Like if we choose 30, we'd have 40 minus 60, so we'll have minus. So this tells us that this is that's our 1. So that's going to be y is equal to 20, and of course x is equal to 20. And so it's a very elementary problem, but that's what we're looking at. But it's the same process for all of these. But it's going to be different equations, of course, varying upon what is being asked.
But the same equation.
Yeah. So anyway, what happens on this one here? Here's example 2. We'll quickly go over this. Everything is written out here. You have a trial and error rectangle has a perimeter of 71 feet. What length and width should it have so that its area is maximum? What is the maximum area? And so there's a trial and error thing here, and then you have the equation. So here's your equation, 2L plus 2W equals perimeter are 71. And if you solve for, in this case, W, you get W equals 35.5 minus L. And then to maximize our area, so W of 10, in fact, that is not, this is just using this, but you can set that up as a equation. So you have area is equal to length times width. And so we're going to have, we have area is equal to well, width is 25 point, so we can substitute in here. So we can put 35.5 minus L times L times L, and then we go ahead and distribute this out. We get 35L, 35.5 L minus L squared. And so if we go ahead and take the first derivative of this, A prime is going to be what? 35.5 minus 2L. And if we set that equal to 0, we say 0 equals 35.5 minus 2L. So 2L is equal to 35.5. So 17.25. So L is equal to 17.25. And then you can find from that 2L plus 2W. So 2 times that is going to be 35.5, right? Mm-hmm. And so W is going to be also the same thing, right? Yeah. So you're going to talk about having a square. Is it 0.75 or 0.35? Is it 17.25 or point? So it's 75, yeah, so it's 0.75, there we go. So I did that wrong. But that's it, so it's the same type of problem, really. Erase this here. Okay, so here's another one. Find two positive numbers that minimize the sum of twice the first number plus the second if the product of two numbers is 288. Whoa. So it's the same type of thing here, that you have those, and you end up getting finding a critical number, and the value is going to be 12. So 12 times what is 288. So if you divide 288 by 12, you get your second number. And so that's what you have. So it's the same sort of thing. Now we get to example 4. Open box is to be made from a piece of metal 16 by 30 inches long by cutting out squares of equal size from the corners and bending up the sides. You remember us doing a problem like this in pre-calculus last year? You do?
Yeah.
You remember something like this? Because I don't remember if we actually did one like this in pre-calculus last year. But
I think we might have looked at it.
Yeah, we might have looked at it. But what you're trying to do, you're trying to determine what size square should be cut out to create a box with greatest volume, and then ask what is the maximum volume. So how would you set that up, what is your equation for volume? Volume is what? What's your equation for volume? It's a basic formula. What is your volume of a box or rectangular prism? Length times width times height.
Only the inside.
What'd you say?
The inside.
Yeah. What it is, you're taking this box and you're folding up the sides of that. Yeah, we did talk about this last year, where we cut out and what happens is, depending on what area you cut out, what you're doing is you're going to fold up these flaps to create an open box with volume. And so what you're doing is you're creating an equation for that. So how do you represent? You're trying to maximize. How do you represent the volume of this box? Using this. So our volume is equal to, how do we get our length? What's our length?
30, but you have to take out the little
Yeah, so it's 30, but minus this x and minus this x, so it's going to be 30 minus 2x. And what is going to be our width of the box?
16 minus
16 minus 2x. And what is our height of the box? We fold up the flap. How high is our box? It'll be x. So here we have length times width times height. So let's go ahead and distribute this and get what that is. So our volume. Now in pre-calculus, what we would do is you just figure out this equation and use a calculator and plug this in the calculator, find your maximum in the graph. But in calculus, we're going to handle this differently because we're actually going to be able to use our calculus to solve this without a calculator. And so what we have here is we have 30 times 16, which is going to be, we want to do it without a calculator, but that's, so 30 times 15 is going to be 480. Is that right? 3 times 16 is 48, so that's 480, right? And then minus 32x and minus 60x. So 32 and 60 is going to be minus 92x, right? And then we have 2x times negative 2x would be plus 4x squared. And the last thing we're going to do is multiply all this by x. So our volume is going to be 4x cubed minus 92x squared minus 92x squared plus 480x, is that right? And then now, if we take the first derivative of this, what is our first derivative of this? Volume equals 12x squared, okay, good. Minus 184x, okay, good job. Plus 480. Okay, if we set this equal to 0, we would have it, right? So we know 12, I guess 12 is factorable, all these things. So 12 times x squared, what's 184 divided by 12? Okay, we know that's 1 there, 12. So we get 6, 4. So 12 goes into 64. 1, 2, 3. Is that 4 times? 5? Yes, I think it is 5. It's 5.
It's like 15.
5, yeah, okay, that's good. So we have minus 15x, and then 480 divided by 12, that's going to be plus, I should know what that is, that's going to be 40, right? And so now we have something that we might be able to factor if we set 0 equal to x squared. Well, let's go ahead and, yeah, x squared minus 15x plus 40. Is this factorable? I hope it is.
The only thing I can think of that equals 3
So 3 and
Yeah, I don't think that's.
40, so negative 4. Yeah, 4. Negative 4, and it's going to be a negative negative, right?
Yeah.
And negative 4 and positive 4, that's going to be 14. Man, it would be convenient if this thing was 14 instead of 15, wouldn't it be? Is that really it? Yeah, that's it. We might have to use quadratic formula. 12. Well, actually, 12 and 60 is 5. So it's not exactly 5 either. It's like,
It's a little over, I think this is.
yes, 5. So this would be like 12, that'd be 60, and that'd be 4. So we have 4, bring down this. Then this would be, yeah, so it's going to be some decimal thing. So it's going to be really hard to get this exactly right without a calculator is what I'm saying. But really, if you find the quadratic, you could use the quadratic formula for that. And probably what we're going to do tomorrow is just kind of finish this out, work more tomorrow, actually Monday, right?
Oh, yeah. It's Friday. How
It's
did I
Friday,
do
yeah.
that?
Yeah, this one here, 5, is more complicated. And what there is on your final test, your final exam, a problem that gives you an equation where you have to, I think, maximize or minimize your cost or something like this by just finding a derivative of a function and using the candidate test. So we'll just work on that tomorrow. Thank you, class.